hydrodynamics. So there are a few definitions which we have to learn. One is viscosity. So you have always learned or you have always heard about viscous liquids. You can see that water is less viscous when compared to honey. So what is viscosity? It is a property of a liquid. So it is the property of a liquid which tends to oppose the relative motions between its various layers. So we know that you can see that when a liquid flows, you can classify into each liquids. So there, if you have a layers like this, so we can see that the this upper layer tends to pull the lower layer forward. But the lower layer, what it does, it tends to pull the upper layer forward with less acceleration and thus retards its motion. Thus, the two adjacent layers behaves as if there is a friction between them. So once again I repeat, viscosity is a property of the liquid which tends to oppose the relative motion between its various layers and the viscous force is the force that comes into play in a viscosity is called the viscous force. Next is the velocity gradient. The velocity gradient is defined as the rate of change of velocity with distance. So you always know that what is velocity gradient. Is nothing but rate of change of velocity with distance. So you can write the unit. You know velocity's unit is meter per second and distance is again meter. So velocity gradient will have per second as a unit. Now we have to derive the mathematical expression for the viscous force. So we can just write mathematical expression for viscous force. According to Newton, the viscous force on a certain layer of liquid is directly proportional to 1. Area of the layer, and 2. The velocity gradient at the layer. So how do we write this? F is proportional to area A and it's also proportional to the velocity gradient dV by dx, or F is equal to some constant eta A into dV by dx. And this eta is called the coefficient of viscosity. Now to define coefficient of viscosity, what we do is we take this equation Substitute A as equal to area as equal to 1. dV by dx as equal to 1. Then what will we get? F will be equal to eta. So now we can start defining the coefficient of viscosity as the tangential viscous force. Okay. So coefficient of viscosity is the tangential viscous force acting so A we have put here 1 acting per unit area of a liquid having unit velocity gradient in a direction perpendicular to the direction of flow. So it's very easy to remember. You just have to know the formula. F is equal to eta A into dV by dx. And if you put A is equal to 1 and dV by dx is equal to 1, then you know that F is equal to eta. So our coefficient of viscosity is defined as the tangential viscous force acting per unit area of a liquid having unit velocity gradient in a direction perpendicular to the direction of the flow. And the unit is eta, we can write eta is equal to what? F divided by A into dV by dx. By A into dV by dx. So let's write the unit. For force it is Newton. Area it is meter square. And dV by dx it is second raised to minus 1. We have looked into. So it is Newton second per meters square. Now what is streamline flow? Okay, next is streamline flow. So you have seen goats, no, going in a flow, like they go in a crowd. So they all go in a pattern. Similarly, this streamline flow means if one particle is moving forward, the other particles also proceed with the same velocity without crossing each other. That is also called the orderly flow. Turbulent flow, so you know it's just the opposite of it. It is not orderly flow, it is a zigzag. The flow is somewhat like a zigzag manner. It happens if the pressure difference between the two ends of the pipe is very large, or if there is a constriction in the pipe, then the velocity of liquid becomes too large at various points. So it is not the same at every point. So such a flow is called the turbulent flow. So you can always feel that, right? When you are watering a garden, what you do? If you want to move the water forward, or if you want to have a higher pressure, what you do? You close the end of the pipe a little bit so that it moves not in a turbulent way, but in a not in a streamlined way, it moves in a turbulent way. So you have to know the difference between a streamlined flow and a turbulent flow. Now next is a critical velocity. So critical velocity is also associated with this turbulent flow and the streamlined flow. So critical velocity is defined as the velocity of the flow up to which the motion of the liquid remains streamlined. Okay. So it is the motion of the liquid which remains streamlined. Motion of the liquid up to which the liquid remains streamlined. Next definition is Reynolds number. It determines the nature of flow of viscous liquid through a pipe. So what does this tell us? It allows us to determine the nature of flow of viscous fluid through a pipe and is given by R is equal to, Reynolds number is represented as capital R, velocity, critical velocity, then density of the fluid, D is the diameter of the tube, and eta is the coefficient of viscosity. So R is equal to critical velocity, product of critical velocity, density and diameter of the tube divided by the coefficient of viscosity. It has no dimensions. It is a dimensionless number. Reynolds number has no dimension. Next is derivation of Poiseuille's equation. So we'll put it on a different color. Okay. So Poiseuille's equation gives us the expression for the rate of flow of liquid through a capillary tube. So what we get from Poiseuille's equation? It is the rate of flow of liquid through a capillary tube. So we assume certain things here for the derivation. The first one is, we assume that the flow of liquid is streamlined. First one. Second one is, the liquid layer in contact with the walls of the tube is at rest. Thirdly, the tube is kept horizontal so that gravity or gravitational force does not affect the flow of liquid. And last one, the fourth one, the pressure is a constant over any cross section and hence there is no radial flow of liquid. So with these approximations, we are going to derive the expression for rate of flow of liquid through a capillary tube. So we'll just draw the cross section of a capillary tube. So I'll draw it in a different color, the inside portion, the sample portion. So this is another cross section. So this what we are going to do is, this portion is called, okay, so I'll just mark all those portions. This point is x. This portion is x plus dx, and the whole capital radius is r. Okay. So this A, B. So consider a liquid flowing through a capillary tube AB of length L and radius R. And the maximum velocity will be at the center of the capillary tube, and at the walls we have assumed that it is equal to 0. Now what we are going to do, we are considering a level x. Okay, what we said earlier is x. Okay, from the axis center. The outer layer, we are considering a thickness of dx. So the other layer is at a distance x plus dx from the axis. So we are considering a layer x from the axis and another layer x plus dx from the axis. Now what is the tangential force acting in the opposite direction to the direction of flow? F is given by eta A dV by dx. So here you can see that since we are taking the opposite direction, we can just put it as F is equal to minus eta A dV by dx. Let's put it as equation 1. Now we know that we have to consider the cylinder. Okay, so area will be equal to 2 pi. You have considered that x with small value. Okay, 2 pi x into the length of the capillary tube. Therefore, substituting in equation 1, F will be equal to minus eta 2 pi x into L into dV by dx. Now, what is the force at the end of A? The force at the end of this A will be pressure into area. So this we give it as 3. The force at the end of A is F is equal to pressure times area. Area, you know, this is a circle. Here end A is a circle. So it is pi. You're considering that x portion, pi into x square. That's my equation number 4. Okay. Therefore, now you have 3 and 4. Both are force acting. So now we can equate them as minus eta 2 pi x L into dV by dx is equal to P into pi into x square. So what is my dV by dx? You can cancel many things here. See, pi can be cancelled. 1x can be cancelled. So we have dV by dx is equal to P into X divided by 2 eta L with a negative sign. So this is my equation number 5. Or we can write dV is equal to minus Px by 2 eta L into dx. Now integrating. If you want to get the whole of the volume, integrating 6 we have V is equal to minus Px x square. This constant is minus P divided by 2 eta L into x square plus some integral constant k. That's my 7th equation. Now how do you find this k? To find k, what we do? We put x is equal to r at V is equal to 0. You know the full volume. So what is k equal to? So k will be equal to, V will be equal to 0, no? So put x is equal to r. So it is, so I'll just write that way. So V is equal to 0 is equal to minus P x for x what you do? You write r. So r square divided by 2 eta L plus k, or your k is now equal to P r square divided by 2 eta L. That's my equation number 8. Substituting 8 in 7. That is V is equal to minus P x square by 2 eta L plus P r square by 2 eta L. Or you can take that P by 2 eta L as common factor. And what you have inside? R square minus x square. That's my volume, total volume. That's my equation number 9. Okay. So what I have done here is when you integrate it, you get x square by 2. Okay. So this becomes minus P for eta L. So here also I have to make that correction, 4 eta L. 4 eta L, 4 eta L. So here also 4 eta L. Okay. Now what do you have to have? The rate of flow of liquid through the whole tube. So let's put this as Q. That will be equal to, you have to integrate this again, okay? Or we can just put it as capital V itself. Integral. So from where to where? 0 to R. Okay, one sec. So what do you get here in equation 9? Here we get the velocity of the liquid for a layer of radius x. Okay, this x. X. Okay. Now the volume of liquid between two layers per second. We can put it as dV is equal to two pi into x dx times the velocity. So now we have to substitute this equation 9 in V here. Okay. So it is equal to 2 pi x dx into p by 4 eta L into r square minus x square. Or you can just cancel this. 2 and 2, 4 here. You can get as p by 2 pi. Okay. So you can just take this x dx inside. Is r square x dx minus x cubed dx. That's my dV. So we can write the rate of flow, this rate of flow of liquid to the whole tube. That is V is equal to integral 0 to R P pi by 2 is constant R square x dx minus x cube dx. So this we can get it as pi p by 2 into r square into x square by 2 minus x raised to 4 by 4 from 0 to r. Or you can put it as pi p by 2. So you just have to put 0 for x and also r for x. So it will be r raised to 4 by 2 minus r raised to 4 by 4. So it is nothing but equal to, this will become r raised to 4 by 4 into pi p by 2. So it is pi p r raised to 4 by did I forget something? Eta LV, no? Eta L. Just I've forgotten certain things. To eta L. So it is 8 pi eta L. So that is my rate of flow of liquid to the whole tube, or my coefficient of viscosity eta is equal to pi p r raised to 4 divided by 8 LV. So this equation is known as the Poiseuille's equation. Okay, please do study it. It's very important. Any doubts, please do ask me.